Hello, today we continue our discussions on mathematics, the integral calculus part, and we have picked up for discussion today a part of integral calculus that is called integration by successive reduction, which also is known as reduction formulae. So I repeat, this is integration by successive reduction, and it's also known as the application to integration of a class of formulas called reduction formulae. We'll gradually build up the lecture by trying two familiar integrals and then seeing how the concept of reduction formula just creeps in. Now for that, let us start with, let's try to integrate tan x to the power of 4. How do we do it? The process is very simple. We write this as being equal to integral tan square x into the next tan square x is sec square x minus 1 dx. Now this is nothing but tan square x sec square x dx minus tan square x. Now here this can be seen that if I substitute z for tan x, this is z square and this is nothing but dz. So this is z square dz. What is z? Z is nothing but tan x minus integral this sec square x, tan square x is nothing but sec square x minus 1 dx. So this drops down to z cubed over 3, which means tan cubed x over 3 minus integral of sec square x is tan x. Minus and minus gives a plus. 1 dx integrates to plus x, and of course we can put a constant of integration. So this is understandable. Steps again. Tan 4 is tan square into tan square. This tan square is written here. Sec square dx minus tan square into 1. Fine. If I take tan x as z, then this is tan cubed x by 3 minus the tan square is written as sec square x minus 1. So minus tan x and minus minus is plus. When I integrate a plus 1 dx, it becomes x. We can sum it up by adding a constant of integration. Now we will raise the index of tan not to 4, but let us say we raise it up to 6 and see what happens. We obviously expect something very similar, but we will do it. We will do it because it is just one step away from what we have done so far. So we change the problem to integral of tan x to the power of 6 instead of tan x to the power of 4, tan x to the power of 6. So now we change our focus to I6. Let I with the sum of 6 be equal to the integral of tan x to the power of 6 dx. Now this can be written as earlier as tan to the power of 4x into tan square x, that is sec square x minus 1 dx. This is tan to the power of 4x sec square x dx minus tan to the power of 4x dx. Now when I shift my coordinates, we see that this is a very, very simple reduction, and we see that I6 can be made to depend somehow on I4. By the same terminology, we can denote this as I sub 4. This integrates to, if this is Z, my friend here is dz, so this is z to the power of 4, so he becomes equal to z to the power of 5 by 5 minus I4. This is of course tan x. So this is the result for I6. Tan x to the power of 5 divided by 5 minus I4, which we have evaluated just in the previous example, and that value can be just substituted. Now, this leads us to believe that perhaps instead of taking very specific cases one by one, if we take an index of tan x to the power of n and see what happens, how an integral of the form tan x to the power of n can be made to depend on same type of integral with a lower index, and that is why these formulas are called reduction formula. We will now get the real flavor of a reduction formula if we write the first problem. It's going to be simple because we build concepts starting from simple examples. Concepts cannot be built by starting from complex examples. So it's very logical now, having done 10 to the power of 4 and 10 to the power of 6, it is very logical for us to say, let us say that what is the process of evaluating and what is the result of tan x to the power of x, tan x to the power of n. As before, we will designate this as I sub n. I sub n. That's fine. Now, this can be written as, in line with what we have been doing so far, tan x to the power of n minus 2 and tan square x dx. There is no problem here. That is tan x to the power of n minus 2 into tan square x. This gets across to tan x to the power of n minus 2. We write it like this. And tan square is of course sec square x minus 1. There. This breaks down to tan to the power of n minus 2 x dx into sec square x. We'll put the sec square x first, minus tan x to the power of n minus 2 into 1. So that is written just as it is, tan n minus 2 x dx. Now, going by whatever we substituted earlier, if we call this as z, then this is z to the power of n minus 2 and this is dz. So, we can call this dz because if tan x is taken as z, this is z to the power of n minus 2. So, integral of this dz minus this is I sub n minus 2, because here is the reduction. If I sub n were to be tan x to the power of n, then it stands to reason that tan x to the power of n minus 2 is I sub n minus 2, nothing more, nothing less. So this can be integrated as tan x to the power of n minus 1 divided by n minus 1 minus I sub n minus 2. This is In. Now here is the first instance where the meaning of a reduction formula emerges. We have related the I sub n, that means tan x raised to the power of n, has been related to a similar looking integral, but with the index coming down by 2 notches. This is I sub n minus 2. I sub n minus 2, and that is why this is called reduction formula or integration by successive reduction. One can see that if every n here is changed to n minus 2, then this fellow can be evaluated and this fellow can be made to depend on I sub n minus 4. We'll do that. We'll just do one more step. Let's see. So having said that, if we write this on top and we write I sub n is equal to tan x to the power of n minus 1 divided by n minus 1 minus I sub n minus 2. Now, if we replace every n here by n minus 2, then we can write I n minus 2 is tan n minus 3 x divided by n minus 3 minus I n minus 4. Every n is replaced by n minus 2. This ultimately would give us an expression for I n in terms of I n minus 4. So there are 4 reductions in the index, n to n minus 1, n minus 2, n minus 3, n minus 4. So if we put back this expression here, we will ultimately get I sub n is equal to tan x to the power of n minus 1 divided by n minus 1 minus, for this we will write tan x to the power of n minus 3 over n minus 3 minus I n minus 4. On simplifying, this becomes this term minus this term but plus I n minus 4. So the flavor or the trick, we could say, is to keep on generating similar integrals similar to I sub n, but the indices reducing successively by either 2 or 1 step. We will see more examples and we understand better.